3D virtual curve creation on and around physical objects is a fundamental operation in many graphics applications, such as 3D sketching, 3D modeling and 3D measurement. They are demonstrated in some existing works. The recent advance in mobile augmented reality allows to use a mobile phone as a 3D pen to create 3D curves. However, mobile phone is different from pen in size, weight and shape, and it does not have a predefined input point as pen tip. So when use mobile phone to draw 3D curves, different users define the input point and hold the phone in different ways. Meanwhile, when creating curves closely interacting with real-world objects, mobile AR often suffer from many errors due to limited visual features. Indifferent input point and phone grip will lead to tracking error in different levels. So we conduct two studies to figure out these two problems. First, we conducted an elicitation study on input point and phone grip. We ask participants to find the input point of a phone, and hold the phone comfortably to create 3D curves in 10 scenarios. We collected 7 input points, and corresponding preference percentage. The top 3 preferred input points are top left corner, back camera and bottom left corner. We also got 6 phone grasps, and corresponding preference percentage. We found participants usually pair the input point and phone grip together. These are the top 3 preferred pairs. Second, we ran a quantitative study on tracking errors of ARKit. We focused on the top 3 preferred input point and phone grip pairs from the study 1. We created 3D curves with mobile phone using ARKit in similar scenarios to study 1. A mocap system is used to get ground truth data. We categorized errors into global world drift, local accumulated drift, local sudden loss track, and local short-term track loss. Among top 3 preferred pairs, global world drift and local accumulated drift happen frequently. We found the choices of input point and phone grip have an effect on tracking errors. TLC I had the smallest errors considering types, frequency and measurement. So for users holding a mobile phone in right hands, we suggest to use this pair for 3D curve creation tasks in mobile AR, both for natural interaction and low initial tracking errors. However, the tracking errors cannot be ignored, since they lead to undesired curves. So we present a system supporting both in situ 3D curve construction and interactive curve refinement to reduce tracking errors. To ensure eyes-free interaction, we propose a special pan gesture to start and finish drawing, with vibration feedback for activation. Then the user uses the phone like a 3D pen to create 3D curves. The original result contains a lot of errors. They are world drift, short-term track loss, sudden track loss, and accumulated drift. Our system first provides an initial correction removing sudden and short-term loss track. For world drift and accumulated error, our system let the user interactively correct them. The user can remove world drift by relocating world anchor, quickly remove accumulated drift by adding point constraint, and an optional 2D sketching for elaborate refining. For world anchor, the user taps a point on the plane detected by our system to locate world origin. With snap on, world anchor can be located snapping to edges. With snap off, it will be moved on the plane freely. The user can also taps 2 rays from 2 views starting from screen to locate world anchor. The user can use a swipe gesture to rotate the world anchor. For point constraint, the user taps a point on the curve, and locate a target position also using ray plane intersection or 2-ray intersection. For 2D sketching, the user drags on the curve to select a segment, then freeze the camera view, and draw a desired 2D curve. Then our system updates the 3D shape of the selected segment with respect to the 2D curves. With these interactions, a desired 3D curve closely interacting with physical objects is created. We demonstrated the usefulness and effectiveness of our system for 2 applications. One is in situ 3D drawing, the other is direct 3D measurement.